quantization where I have correspondence between density matrix and Wigner function, which is defined as partial Fourier transform. I usually skip H bar, but here, at least in last lecture, I kept it because we were discussing classical limit. It was obvious that the corrections, which corrections vanish when H bar goes. So then we discussed that Wigner function is a particular case of Weyl transform, and actually for any operator, you can define what's known as Weyl symbol, which is same partial Fourier transform. So we interpreted Wigner function as a quasi-probability distribution in the sense that if you want to calculate expectation value of any operator, this is just an integral over phase space, and I just remind you again that nothing is limited to one particle, so everything here are vectors in my phase space. It's an integral over Wigner function times the Weyl symbol. We also discussed that there is a natural representation, which is called Bock representation, where x goes to x plus IH power over q d by dt. P goes to P minus IH power over 2 d by dx. And this Bock representation just naturally produces Weyl symbols in the sense that if you substitute these Bock operators into our operator omega, will automatically generate Weyl symbol without any integration. And finally, important concept was that there is a Weyl product. So if you have product of two operators, then the Weyl symbol is given by so-called Moyle product, which is minus H bar lambda 2. And in particular, what is very important are commutators, and commutator of two operators is minus IH bar times the Moyle bracket of two symbols. Which is defined, so the Moyle bracket is defined as 2 over H bar, sine of H bar over 2, 1, lambda. And lambda is symplectic operator, it's just plus one bracket. Good. And then we discussed there are some examples how we can use all this to represent quantum systems. So in some sense, this is a complete representation of quantum systems. So, and someone actually asked me a question yesterday. So, was it really applied to say the equilibrium systems? And not that I know of. So this might be an interesting application. Try to see whether one can get some useful approximation schemes by applying this to the equilibrium density matrices. Again, so main use of this formula probably will come from proximity to classical limit. Okay, so today I want to basically start by generalizing or extending the whole thing to coherent states. And for the most part of remaining two lectures, I will stick to coherent state. Because we will mostly work, when we think about many particle problems, we think about usually second quantization language. And that's where coherent states appear. So I'll just basically, now is almost no proofs, with occasional proofs, we'll just give you an analogous result. So we will define Weyl symbol, but now it's a function of my complex phase space variables, complex amplitudes. So think about this as growth rate. Exactly in the same way. So we'll have it as an integral over d eta star. Here we have a minus eta over 2 omega a plus eta over 2. And here we have 1/2 eta star a minus a. So this will be analog of a Fourier transform. So everywhere here, by this complex integral d eta star, I understand this real part eta, imaginary part eta divided by pi. This is just one of the conventions.
In the exponent, do you mean eta star a minus a star eta, or do you really mean
Yes.
different?
Oh, yeah, sorry. You're right. Yeah, it's purely imaginary. This will be, actually, if you use this mapping between oscillator and A, then you will recover, you'll just see that this is equivalent transform. But I want to keep it independent because these A's don't have to come from any oscillators. These are just bosonic fields, these canonical relations. So it's very convenient to, we usually work with normal ordered operators. So let me just write this expression when my operator is normal ordered. So it means that I have all A daggers here and all on the left and all A daggers on the right. Then this is really trivial, right? Because I know that A acting on coherent state, say A plus eta over 2, is ket A, will be just A plus eta over 2 times this coherent state. I get just a number. So in the same way, A dagger acting on this coherent state will give me A star minus eta star over 2, so this is just numbers. So the only thing I need to do is an overlap of two coherent states. Well, and that's very simple. I leave it as an exercise to prove, but it's in any standard textbook. So I have minus 1/2 of this squared minus 1/2 of the other one squared times overlap of A star minus eta star over 2 times A plus eta over 2. So the overlap of coherent states is very simple. So we just take e power this star times this, and these two guys come from normalization. You can just check that if I have same number here and here, I'll get 1. Okay, so let's just see what it gives us. So it's e to the minus 1/2 mod A squared times 2. This comes from A squared. The other one. Then we have also minus 1/4 mod e to the 2. I have 1/8 from here and 1/8 from here. Then I have, well, now I have to be, I guess, careful with signs. So I just write it down. So I will have what? Eta star A, 1/4 A eta star. This is from these guys. Then I have A star eta from these two guys. Okay, but those will probably cancel with these two. So that's good. And then from the remaining two guys, I will get e to the mod A squared. I will get e to the minus mod eta squared over 4. So this will cancel. And the final ingredient, I will see that it will be exactly minus sign of this thing. You will have minus eta star over 2 eta, here plus eta star. So in the end, I'm getting very simple expression for normal ordered operators.
Is there 1/2 missing on the top line? 1/2 A star? Otherwise, we understand how.
Where? Here?
Yes.
No, because it's just overlap of this two.
Okay, so how do you get the quarter?
Oh, because I have 1/2 here and 1/2 here.
But that would. give you the according to the eta star, not in the a dot eta.
Wait, here I have 1/2. Okay,
The third term in the
oh, the third term came from here, but it's cancelled by the same term from here.
Oh, okay. Oh, that, okay.
Yeah, this actually I should have figured it out. So you don't need cross terms, just cancel between these two.
Yes,
So
okay.
sum of these two is just these guys.
Okay.
But then I have cross terms coming from this product, but these cross terms are exactly minus sign of these cross terms. So at the end I get very simple Gaussian integral, and we like Gaussian integrals. So that's why coherent states in sense are nice. So it's yes, it's omega of a minus eta over 2 a star, sorry, minus eta star over 2 a plus eta over 2 times e to the minus mod eta squared over 2. Right, so the only thing which remains is eta squared over 2. I have 1/4 from here, 1/4 from here. So now I can erase everything, and I just see that my while symbol is just a Gaussian integral. So, and before showing examples how it works, let me just immediately, again without proof, write Bock representation. So you can find some hints of the proofs in the notes. So I'll write that A will be alpha plus 1/2 d by the alpha star. I guess there's almost nothing else you can write, because you know it should be symmetric, and the sign is fixed by commutation relation. So you have to choose plus and minus, and you know the commutator of the dagger should be plus 1. So let's just check how it works. So, and I'll show you a couple of examples. So let's first calculate while symbol of a dagger A. So first I will use my Gaussian integral. So what I will get is mod alpha squared. Sometimes I alternate, sorry, alpha and A. I try to stick to alphas because otherwise it's too messy. Minus mod eta squared over 4. So that's what I'm getting from this guy. It's just product of this times this, right? Times e to the minus mod eta squared over 2. And then I have to take integral over the eta star. Well, this is easy. So my Wigner function, we know, is normalized. I didn't check it, but you can check that as in coordinate momentum representation, it's normalized. So this integral, the first integral, will give me just mod alpha squared. And for the second integral, well, average of eta squared is just 2, just because I have 1/2 here. So that's minus 1. Well, now let me do the same with both operators. So I have to use alpha star minus 1/2 d by the alpha times alpha. Again, I don't write any derivatives here because there is nothing on the right, so I'll get zeros. So I will get alpha star alpha minus 1/2. It's the same. So let me do another example. A dagger, AA. It's basically m squared, normal quadrant squared. So first I do Gaussian integral, and I have to take integral over d eta star. I will use a star minus eta star over 2 squared times a plus eta over 2 squared times e to the minus mod eta squared over 2. These integrals are much nicer than in coordinate momentum representation. There we had oscillating exponents. We had to take derivatives of delta functions, just worry about regularizations and so on. Here everything perfectly converges. So again, there will be first contribution coming just from A's. Sorry, I use alphas like before. So just alpha to the 4. Then obviously, when I take a Gaussian integral, only even power, I need same number of eta stars and peters. So next term will be when I have one eta star from here, one eta from here. And I can do algebra in my head, so I will get twice product of alpha star, eta star over two cancels. I get just product of these two. I get the product of these two. Average of eta squared is 2. And then I get minus sign. A minus here and plus here. So I get minus 2 alpha squared. And then the final contribution will come from only from peters. I will get plus, because I get square of this, square of this. I will get 1 over 16. Then I will get 4 from each eta squared. I'll get 2 from contraction. Right? I can use Wick's theorem. It's a Gaussian integral. If I have eta star, eta star, eta, eta, there are obviously 2 contractions. So I'll get 8 overall over 16. I will get 1/2. So, and as you might guess, I can reproduce the same integral, the same result using Bock representation in half a line instead of 1 line. I just see that I will get again 1 alpha to the 4th. I'll get twice the product of these two, but d by the alpha acting on alpha squared gives me 2. Get minus 2, 1 alpha squared. And I'll get 1 over 4 second derivative of alpha squared is 1/2. Same result, but I didn't have to do any integrals whatsoever.
Any question? Does the Bock representation work if the operators are not normal ordered?
Yeah. Yeah, that's another advantage, by the way. So if you have non-normal ordered operators, this is a little bit involved. So the easiest way to use integrals to first bring operators to normal order and then take Gaussian integral. When I have non-normal, well, let's actually do this. I mean, why not we check this? So suppose I want to do A dagger A dagger A. This is non-normal order. This is just n squared. So of course I know this is the same as normal ordered n squared. Then I have to be careful, plus and minus, plus n. Right? Because this is the same as this I can write as A dagger A plus 1. So in some sense I can immediately read the answer, and I actually want to do it because later I will use this result for one symbol of n squared. So why don't we do it now? Plus 1/2, and then I will get plus extra n, which is mod alpha squared minus 1/2. Oh, I cannot write here. Okay. Plus mod alpha squared minus 1/2. And then at the end I get something very simple. I get basically n squared minus n. So if I use Bock representation, then I don't need to do any of these tricks. Just write alpha plus 1/2 d by d alpha star, alpha star minus 1/2 d by d alpha, and then I write alpha. So it looks a little bit more complicated, but it's still doable. We can do it just line by line. So when I look into these guys, I will get just alpha star alpha minus 1/2. So now I will get what? I get alpha times this, minus 1/2 alpha, but then plus 1/2 d by d alpha star of this. This gives me plus 1/2 alpha. So my half alpha cancels. So after considering this whole bracket, I will get alpha squared alpha star. I don't know if it's too low. It's alpha squared alpha star anyway. So now I just need to take this derivative, and then what I will get is alpha to the 4th minus d by d alpha of alpha squared is 2 minus alpha squared. So it works. So you can also have an alternative Bock representation, and again it will be important later, today, tomorrow. We can change signs here, For example, we can write it minus 1/2 d by d alpha star, but put left derivative here. So which left derivative means that it acts on the operator which is on the left. It's like integrating by parts. And you can check that, of course, results will be the same. Okay. So, and then the last ingredient will be Moyle product. And again, you might guess that if I have two operators, omega 1, omega 2, then it will be omega 1 e power lambda c over 2. Remember, I introduced this guy before, omega 2. I just remind you again that lambda c is a coherent state Poisson bracket. It's d by d a, d by d star, or alpha star, minus d by d star, d by d. So again, instead of doing any calculations, let's just check that it works only for one, for a dagger a. Then we want to write that this is alpha star, e to the minus lambda c over 2 alpha, which is the same as alpha star times 1 minus lambda c over 2 alpha. Again, there are no other terms because no high order derivatives act on alpha. And well, here we should also write plus lambda c. And then when we have lambda c, yes, so only a minus part of lambda c will give me a contribution. So I'll get minus 1/2. So it works again. And then you can check yourself that if you consider this high order correlation functions, it works again. So cannot breathe. All right, so of course, as in coordinate momentum representation, Wigner function and Weyl symbol come together. Where is this? So in a sense that expectation value of any operator, omega, is equal to integral over d alpha star, Wigner function of alpha star times Weyl symbol. The proof is the same, and it's very simple. So just basically, in one line you can convince yourself that it works. Okay, so let me now go into a few examples of Wigner functions. And of course, we start from something very simple. We start from a vacuum state. In a way, you already know the answer for the vacuum state, because vacuum state is a ground state of a harmonic oscillator. But let me just do it independently. So I take my density matrix as a state with no particles. And then if I want to calculate Wigner function, I just substitute this density matrix here. And then, well, I know what my coherent state is, right? So my A is just sum over n, A power n, or actually A to the power n, acting in vacuum. So if I want to times, sorry, e to the minus, use alpha again, e to the minus alpha squared over 2 from normalization. So you just see that overlap with vacuum is just given by minus 1 alpha squared over 2. So if I want to compute my Wigner function, I will get an integral, and I will get e to the minus 1/2 of this squared, 1/2 of this squared. We already did this calculation. It's e to the minus mod a squared minus mod e to the squared over 4. And then I have e power 1/2 eta star A alpha minus eta alpha star. So it's a Gaussian integral, and I can complete squares. So let me use a trick which is not, I think, completely mathematically rigorous, but which works. So I just use the fact that my eta and eta star are independent variables, and then I can clearly write this expression in the Gaussian minus eta squared over 4 plus 1/2 eta star alpha minus eta alpha star. I can write in the following way: minus 1/4 eta star, let me just try to get it right, minus 2 alpha star eta plus 2 alpha. See if I got signs right. No, I got them wrong. And then I will get extra plus alpha squared, so we need to subtract minus alpha squared. And now I will call this my new eta as tilde, and this is my new eta tilde. So as you see, this is not very rigorous in the sense that these are no longer complex conjugates, but you can convince yourself by going to the real part and imaginary part and integrating separately that actually this works. So you can do even this sort of completion of the square. So if I do this, I will see that I get extra minus 2 alpha squared, and then I will get a Gaussian integral, which will give me 2. It will give me 2 because it's mod eta squared over 4. So at the end, I'm getting a very simple result. This whole thing is just 2 times e to the minus mod alpha squared. So and this is nothing but our vacuum fluctuations. So if we think about this Wigner-Weil quantization, that the ground state is not dead. It has particles. Right? Because if we calculate expectation value of alpha squared, we'll get 1/2. And of course, there is no contradiction with anything, because if you want to calculate expectation value of A dagger A, then this will be, as we just figured out, it's alpha star alpha average over the Wigner function minus 1/2. So this 1/2 will be killed by this 1/2, so we don't have any contradictions. But if you think about a little bit ahead, we think about future, this 1/2 is time dependent, this 1/2 is just 1/2. So once you start considering dynamics, these vacuum fluctuations will be very important. Okay. So again, as an optional exercise, I leave it to you to show that if you consider now a thermal density matrix for an oscillator, then your result is again very simple. It's still a Gaussian. Just write it down. It's 2 hyperbolic tangent for omega over t times e to the minus 2 alpha squared hyperbolic tangent. The same page one. So when temperature is 0, this of course reduces to what I just erased. But if temperature is finite, as in the previous case, we just get Boltzmann distribution. Because it's yes, because h bar omega is just energy, and we will get basically energy times alpha squared divided by t. And remember, we discussed in the second quantized form, energy of an oscillator is h bar omega times n, alpha star. Okay. So one more example, which is actually quite important, and which I will go through again in some level of detail, is sketch derivation. This is example of Fock state, because I told you that Wigner function is in general non-positive, but so far I was just showing you nice Gaussians, which work for harmonic systems. So a very simple state, which will be very, very important, is for many stations, is the Fock state. So let me consider my density matrix as the Fock state with n particles. So and let me try to compute the Wigner function. Well, first I need to know the overlap with coherent state. I remember that n is a dagger power n divided by square root of n factorial times vacuum. The square root of n factorial is needed for normalization. Therefore, when we consider overlap with coherent state, which is sum over n, a dagger power n over little n factorial, x to the minus square root over 2 vacuum. Of course, we must have the same n, but then we have to be careful with factorials. We get square root of n factorial here, and we get n factorial here, but then contraction of a dagger and a will give us another n factorial. Overall, I will get 1 over square root of n factorial. That's all what I need. So now, Wigner function for state with n particles, we just integral over d eta star. And here I will have alpha star minus beta star over 2 power n times alpha plus beta over 2 power n. I have 1 over n factorial. I get square root of n factorial from 1. I will get square root of n factorial from the other overlap. And then I will have e to the 1/2 eta star alpha minus alpha star eta. And then I will get overlap of coherent states, which we already computed last time, which is minus alpha squared minus eta squared over 4. Now I will use the same substitution as we did before. Okay, I'll just basically say that eta star will be minus alpha star plus yes.
Is that e to the power of 1/2 eta star alpha minus alpha star eta going to be gone due to the overlap? Not going to cancel out?
Which power?
E to the 1/2 eta
This?
star. No,
This?
1/2 eta star alpha minus alpha star eta.
No, this was no, because there's a difference with operator and density matrix. When I have operator, indeed I have overlap of coherent state. When I have density matrix, I have n dot n. There's no overlap. So yeah, that's right. Okay, so now I will use the same substitutions. I'm completing the squares, and basically what I'm getting from here, I will get minus 2 alpha squared minus mod eta squared. I also want to change, remember it was eta squared over 4, but I want to change eta to 2 eta. Anyway, you can just trust me on this. So after completing the square, what I will get here is 2 alpha star minus eta star, 2 alpha plus eta, and I get extra 4. I did the substitution, eta to 2 eta. Anyway, so this is again a very nice Gaussian integral, and I see immediately that I will get polynomial here, but I have to have same number of eta stars and etas to get non-zero result. So at the end I will get a very simple sum. The answer you can find in the notes. And yeah, so one important thing why I started with all of this. One important thing that you might guess, or you might see that there is an alternating sign. So if I have no ethers, I'll get something positive. If I get 2 ethers, I'll get minus sign. If I get 4 ethers, I get plus sign. So I'll get some polynomial, all contractions of eta squared are just numbers. So I get some polynomial in alphas, which has alternating signs. And it turns out that what I'm getting is known as Laguerre polynomial. So the whole answer would be 2 times e to the minus 2 mod alpha squared times ln of 4 alpha squared, where ln of x is minus 1 power n times sum over n from 0 to n minus 1 power m n factorial squared n minus n factorial x power n. So just to give you a few examples, L1 of L0 of x is just 1, and L1 of x is just x minus 1. There are, by the way, different conventions, whether it's 1 minus x or x minus 1, but doesn't matter. So for 0 particles, we just back to our Gaussian. It's a vacuum state. But already for 1 particle, we are getting something which is not positive, right? Because we get 4 alpha squared minus 1. It's negative when alpha is small, then it becomes positive. And if we have more than 1 particle, it actually oscillates more and more. And then we might be actually even a little bit puzzled. So what happens when we take classical limit, right? So we just believe that if n is big, our Fock state is like a classical state with n particles. We cannot count on that. But you have a very well-known example, which you know very well, of another classical limit, which is WKB approximation. And we know that there we approach the classical limit in a very non-trivial way. So wave function, instead of being localized near classical probability, it actually oscillates like crazy. But whenever we calculate smooth observables, these oscillations don't matter. So if you sketch this Laguerre polynomial, you'll get actually a function which looks very, very similar to a harmonic oscillator. Sorry, not harmonic oscillator, to WKB wave function in any potential. So in this maximum, we of course, so this is mod alpha squared. So in this sense, from at least this sketch, you can see how you recover classical limit. So everything where our alpha star alpha is small will not give contribution with any smooth operator. Well, our operators are smooth. We just computed them. They're a nice smooth function. So everything from this region will give us 0. Everything of this region will also give us 0 because it just decays as a Gaussian. So the only contribution which will come from a saddle point is from this region. But okay, these are words, but if you want to do calculations with this Laguerre polynomial, it's still a very simple state, it's just a Fock state, then you will be in trouble. Because in order to evaluate this integral with n big numbers, say 100, you will have huge sign problem. So, well, and of course, this is a special polynomial which you know analytically, so then probably you can use some analytical tricks. But in general, if you try to use Monte Carlo or any other method, it's very complicated. Yes?
Can you compare the Wigner function of this Fock state to that of a coherent state with the same?
Yeah, coherence. Oh, yeah, it actually was exercise which I forgot to mention. If you have coherent state, then it's just a shifted vacuum. So I actually left this as an exercise. Thanks for the question. So if you have coherent state, square root of n coherent, so that's exactly state with n number of particles, then its Wigner function will be just 2 times e to the minus 2 a minus square root of n squared. So coherent states are much nicer. Coherent states actually belong to the family of Gaussian states. So for them, Wigner function is positive, and you can interpret it as a probability. So what do you do? So, well, sometimes you can say that maybe there is no difference if I have Fock state or coherent state, and then why don't I start from coherent state? Then I can sample my Wigner function very easily, and then I hope that it's like an equivalence of ensembles. If you want, one is microcanonical, one is canonical, there will be no difference. So that's one approach. Another approach, which is a little bit more general, I just want to sketch it, and this is probably will be important if you want to use this as an application, use this method. You can just say, okay, but maybe I really need correlation functions higher than second. So why don't, instead of a Wigner function, I will find a best function in the sense that it will reproduce correctly my first two cumulants. And then I won't worry about anything else. So let's just do this exercise. And of course, this exercise only works when n is reasonably large. So, but reasonably large, what I mean that if you try, say, 5, then already what I'm talking about this is very good. So you know Gaussian.
Sorry, Anatol.
Yeah.
One question before you erase it. I think this is just a
I can restore it.
yeah. Can you just push the argument saying that there are classical operator and quantum operator in your theory, and the quantum operator are the one that varies on shorter time scale, that would be sensitive to the...
Well, unfortunately, it doesn't work. I don't know how to do it, because if I do Weyl symbol, I just show it to you. In some sense, like when I wrote, say, Weyl symbol for like n squared, it was n squared minus n, right? We just had this calculation. So this is in some sense classical part. Remember, my classical limit now is large n. So I have many particles in my state. That's the classical way. So this is quantum corrections, 1 over n clearly. But it's not that it oscillates. It's a Wigner function which oscillates. So it's really subtle. So we always, unless we deal with exponential operators, so these complicated operators, we always deal with smooth operators. Quantum, even quantum corrections are smooth. So, but Wigner function oscillates. So I'm not sure. But as we move forward, there will be more questions than answers, as you will see. So, but this is like basically, if you wish, encouragement to, if you are interested in this, there are lots of open problems, just to say, both practical and so let me try to find a good function for this Fock state, which is nice, and we know nice functions, there are very few. The nicest is Gaussian, so why don't we try Gaussian? So I'll call it, I don't know, Vg of n. And I tried it as a standard Gaussian way. So it's 1 over square root of 2 pi sigma times e to the minus n naught squared over 2 sigma squared. And of course that I expect that n naught should be of the order of m for Fock state, and sigma, who knows what it is. So we need to require that this function correctly reproduces first two symbols, first two moments of n. So we know that average n must be equal to integral over the. I mean, obviously, for a Fock state, there cannot be any dependence on phase. So instead of function of alpha star and alpha, I wrote immediately function of just product alpha and alpha star. So, and I integrate over n. Otherwise, I'll break symmetries, and it won't be a good Wigner function. So I have to integrate now over n. It's like d alpha star d alpha, some factors of pi. And then I have Weyl symbol, I have to be careful, Weyl symbol of n, and then my trial wave function. And this whole thing should be just equal to n. Okay, so I know for Gaussians, I don't need to do all these integrals. I know that this will be a naught, because my Gaussian is centered around a naught. I get minus 1/2. So I just see that I choose n naught is equal to n plus 1/2. So it's slightly shifted Gaussian. And this 1/2 is precisely to compensate for the vacuum fluctuations, which we know in vacuum. So now let me try to do same with n squared. So we already, so this should be exactly n squared. On the other hand, it should be integral over dn. Here we have n squared minus n, because remember, while symbol for n squared was n squared minus n. And then we have again our Gaussian. Well, we know what's expectation value of n squared. It's just n naught squared plus sigma squared, right? Mean squared plus variance. And for n we have just n naught. But we already know what's a naught. So this is the same as n squared plus n plus 1/4. So this is a naught squared. We have plus sigma squared. And then we have minus n minus 1/2. So a naught. So we get it sigma squared minus 1/4. I get very simple result that sigma is just 1/2. So it just turns out that instead of writing this complicated Laguerre polynomial, I can do something much simpler. I can just erase this general result and write that my Wigner function will be square root of 2 over pi times e to the minus n minus 1/2 squared times 2. So, and I just know my former student, Rachel Tripolita, he kept this Wigner function for spin systems. I'll comment how this translates to spins. Well, if you know Schwinger, if you represent Schwinger bosons, if you don't know, I'll talk about this a little bit later today. Then natural state, if you say spin pointing up, it's exactly Fock state of bosons. So this Fock state is actually a Wigner function for my spins. And if you try Laguerre polynomial, you'll get exact results, but you cannot simulate more than a few spins because it just oscillates like crazy. You can try delta function instead of this, and you'll get reasonably good results which work when, say, spin is of the order of 10, 20, or something like that. You try this Gaussian, and when spin is already 2 or 3, so it's not that big, you just get near perfect agreement in observables. So Gaussians are really nice. And the way it works, because if you do this, you actually, if you think about this, you compute the next cumulant, you'll make mistake which will be only of the order of 1 over n squared, or even higher, maybe 1 over n cubed even. So, and even when n is like 3 or 4, this is already reasonably small.
But how does this compare to approximating Fock state by a coherent?
No, you'll get much bigger error.
It's
You'll
worse.
get 1 over n, yes. Well, because coherent state has different variance than Fock state. Fock state has variance 0, and coherent state has variance root n, yes. Well, sigma squared n. So you'll get this mistake. Here we did much better, because we reproduced exactly both mean and variance. So, and actually I think this by the way, you won't find, I guess, anywhere, because it was not discussed, at least I'm not aware of any literature. But I think if you deal with many body states, so suppose you want to use it as a tool, you want to simulate dynamics, then, well, first of all, you need to know what's the Wigner function of initial state. And after that, you try to propagate it in time, one way or another. And then there was, well, I would say 2 methods available in literature. First, you just say, I don't care what the initial state is, I just put some fluctuations by hand. Because I know there are, basically I can estimate that from uncertainty principle, and then just put them by hand, and after that, hoping that my final answer will not depend on sort of details of this noise, I just plug it straight. Another possibility was that you assume that the initial state is non-interacting. And still fine, because of course if you're interested in equilibrium problems, well, you know everything about non-interacting state. But if you start from non-interacting state and turn on interactions, for example, then dynamics is highly non-trivial. But you already know that at least your initial state is Gaussian, you don't worry about this, you worry only about dynamics. And another possibility is that you actually start from non-interacting state, then adiabatically turn on the interactions within dynamical methods which I'm about to describe, and after that you start your dynamics. But actually there is a third way which might be actually a shortcut, is that if from your equilibrium state you know, say, second correlation functions up to second order, so like analog of this will be 2-particle correlation function A, dagger J, and 4-particle correlation functions. So if you know them within any approximation you use, then you can basically find a simple wave Wigner function, Gaussian or whatever else, which is hopefully positive, which reproduces these correlations. And then you know that up to 1 over n squared corrections you'll find. So this is like another way. In general, finding Wigner functions is very challenging. So for simple states you can do it, but in general it's not a simple exercise. Yes.
So I'm wondering, these functions are not always positive, but is there something like a maximum entropy optimization analog that you can...
Not that I know of. I even don't know whether you can write variational principles for a Wigner function, because it's definitely useless to optimize the distance. Because if your function oscillates like crazy, if you try to measure any distance between positive function and this oscillating function, it won't work. So it's obvious that you should sort of remove oscillations one way or another, and I don't know any mathematical procedures. So I don't know. I mean, I think people study this only in the context of very simple systems, basically. Or they just did what I said. So you just put some initial state by hand without much thinking, and then you hope that you are not sensitive to initial noise. It's interesting. If you want to look into equilibrium problems, then this might be actually a way to do it. Okay. So let me just briefly comment about spin systems, and then we go to dynamics and slightly define. So, but again, spin systems. Well, first of all, we work a lot with spin systems in condensed matter, but then we know that we can all very often map various systems like hardcore bosons to spin half particles and so on. And also spin systems are particular examples of more general. So if you want spins are just some generators of SU2 algebra, and you have various SUN extensions, and I think if you understand how this whole machinery works for spin, you can understand how it works for any other group. So, and the idea is very simple. So, actually there were attempts to work with spin coherent states, and I think they were not successful. Well, at least my understanding, they were not successful. And the reason is that once you try to do all these integrals, so spins are compact, you don't get delta functions. And since you don't get delta function, you get something extremely messy. You get just integrals and so on. But there is a very simple way to go around, because I can always use Schwinger-Boson representation of any spin. So I can always choose, like, for example, SZ will be alpha I dagger sigma Z. Let me just write it explicitly, since these are 2x2 matrices. And similarly, I have S plus, which is alpha dagger beta, and S minus is beta dagger alpha. I'm sure you all know about it. If you don't, just check that this representation it respects spin commutation relation. There is one subtlety, that alpha dagger alpha plus beta dagger beta is equal to n, which is 2s. So usually this is a constraint, but for us it's just a Fock state.
So you mean beta instead of beta? Instead of beta?
What?
You mean S plus.
S plus.
Oh yeah, sorry. Yes. Yes. So, but for us this is a Fock state, and we already know what to do with Fock states. So we just discussed. So then we can immediately find a Wigner function, a Weil symbol of any operator using this Bock representation, right? Because we immediately know that alpha dagger becomes alpha star minus 1/2 d by d alpha, and beta dagger becomes beta star whatever minus 1/2 d by d beta. Just as an exercise, let me compute the Bob operator for SZ. It's a little bit complicated, but that's what it is. So it will be 1/2 alpha star minus 1/2 d by d alpha. This is not Weil symbol, by the way, I'm computing. I'm computing Bob operator, so I'm not dropping derivatives. D by d alpha star minus same as beta, and this will be 1/2 alpha star alpha minus 1/2 minus 1/2 alpha d alpha plus alpha star d alpha star, and minus 1/4 d2 by d alpha d alpha star, and again minus alpha d. So if I want to compute Weil symbol, all these derivatives that I said they 0, they 1, and so we see representation of SZ will be basically classical SZ, because we have alpha star alpha minus 1/2 minus same thing with beta. This is beta star beta minus 1/2. 1/2 cancels and I get classical SZ. But if I want to compute, for example, SZ squared, Weil symbol, I have to use now this Bob representation for SZ, square it, and then if I stare carefully into this expression, I will get that this will be SZ squared minus 1/8. And minus 1/8 basically comes from these derivatives. Everything else works. Again, if you're interested in details, I don't want to spend time on this. It's a very straightforward calculation. And moreover, you can just get rid of these alphas and betas completely. You can go back to classical spins, because this is quantum representation. If you want quantum Schwinger bosons, I can write instead classical Schwinger bosons. So I will write alpha star alpha minus beta star beta and call it classical SZ. And then it turns out that if you do some algebra, you can find this answer. Don't see it. Oh yeah, it's here. Then you will find something which looks reasonably complicated, but that's again this expression appeared in literature, and there's nothing you can do about this. This is an operator for the spin, and it looks like this. It's S plus grad minus 1/8 grad plus x dot grad minus 1/2 s. Such a mess. But when it appeared in literature, this expression was derived in a way more complicated. So if it looks complicated, it's still simpler than you can do. So, well, first of all, you see that there is nothing wrong with this. In the classical limit of large S, I reproduce my S, because all other corrections are down by 1/s. My gradient is d by ds, so this is of the order of 1. This is of the order of 1/s. This is of the order of 1/s. This is of the order of 1/s. So I just see in the leading order in 1/s, I have only this guy, and the next order 1/s squared, I have another guy. And in principle, from here, I can I can compute wild symbols of anything. Usually I don't need correlation functions higher than second order, and then you just see you have something very simple. So there's one way that you deal with this. What I found personally is easier that you just continue working with Schwinger bosons. Because this doesn't give you any simplifications. You can express whatever any Hamiltonian in terms of Schwinger bosons and that's it. Moreover, in terms of Schwinger bosons, you can just see it, you can represent anything because well, here you just see that between alpha and beta, right, I put generators of SU2 groups, which are sigma Pauli matrices. I can put generators of SUN group and use the same Schwinger representation, and I'll just get slightly more complicated structure, slightly bigger matrices, but everything works. So I can write my Bob operators, Wigner functions, well symbols, and basically work out this whole phase space picture.
Sorry, I think I missed the connection between the middle line and the bottom line. So the one written.
So this line is the same as this line.
Okay.
But I'm going back from alphas to classical spins. They're the same. So it's easier to go from here to here. So if you substitute for S, say SZ alpha star alpha minus beta star beta, and calculate this, so this is the same as this. I'm just saying that in principle, you don't need Schwinger bosons, there's a shortcut. I actually don't know how to make the shortcut without using Schwinger bosons in between, but I'm sure there is a way. Maybe it's somewhere in the future. So you can apply the whole machinery to spins, study arbitrary correlation functions, and so on. Okay, so just let me now summarize this non-dynamical part by basically contrasting two pictures.
So can you think, I missed, how is the constraint of bosons here?
It's just it's constraint on a Wigner function, not on operators.
Oh, I see.
So my Wigner function should be a Wigner function of a Fock state,
I see.
which is not very nice.
But you might take that.
But I might take this Gaussian, and when my S is already 3 or 4, I get very good agreement. Actually, it's not so bad because if my S1 and 2, my exact Wigner function has 1 or 2 oscillations, right? When I had one particle, S is equal to 1, well, I guess S is equal to 1/2 corresponds to one boson. It's one Schwinger boson. And one Schwinger boson, I wrote down the Wigner function for a Fock state. It was like this, whatever, x minus 1 for n minus 1. So there is only one node. So it means that this function doesn't have sign problem. Well, it has so small sign problem that it's okay. It's just one node. So, and you can see that when S is 1/2, 1, 3.5, it's okay. But when S is 2 Gaussian, it already works. So what is important, not really S to S number part. So when S is equal to 2 Gaussian works well. So in principle, you can basically cover the whole region. So what I want to do now is just contrast these two pictures, two phase spaces. And maybe just highlight that there is nothing secondary in second quantization. So this will be my coordinate momentum representation. This will be my coherent state representation. So we deal with phase space variables Q and P, which have the number of traits. Here we deal with alpha star. And the corresponding operators will be quantum Q hat, P hat. Here we have alpha beta. So we have standard representation. Q is Q, and P is minus IH bar to Q. We have standard representation here, alpha, and alpha dagger is minus pi alpha. We have commutation relations to alpha P beta is equal to minus IH bar delta alpha beta. And what I want to highlight, alpha and beta refer to different particles. Here we have alpha I alpha j dagger is delta ij, and ij refer to different modes. That's sort of the essence of this second quantized picture. We might think about, say, waves in the ocean. We might think about them as particles moving from point to point. This is first quantized picture. Or you might think that we fix the point and look how amplitude of the wave and the phase changes in this point. And this is a wave picture. That's a sort of simple cartoon for first and second quantization. Then we have Wigner function, which is partial Fourier transform. I won't write it down because we just get it here. We have Wigner function here. We have Wald symbol. We have Wald operators. Sorry. Q is Q plus IH power 2 d/p. And here we have alpha for A is alpha minus 1/2 d by L star. And so on. I won't finish this list. So we have model product and so on. Poisson brackets. So basically we have complete analogy between these two formalisms. And the reason I'm I want to highlight this again, that now there's not much time left in the last two lectures. I'm switching exclusively to second quantized language. So when we discuss dynamics, I'll just talk only about this phase space picture because it's more commonly used. But you might understand that everything which I'm going to say about dynamics exactly translates to this first quantized picture. There are some subtleties with factors of 1/2 and so on, but this you can always find in literature. Okay.
So, what about the second quantization of fermions? Is there?
Yeah, that's an excellent question. So, I honestly don't know, because you can actually make all this translation to fermions. Your alphas will be just Grassmann variables. So everything holds. So the problem is that when we want to apply it, say, to dynamics, as I said, the idea that we have proximity to a classical limit, and we can use, we can solve, say, nonlinear classical equations and perturb them. There is no sense, as far as I know, how you can solve nonlinear classical equations for Grassmann variables. So you can just write them down, but you don't know what to do. And that's an excellent open question. So if you want to integrate out Grassmann variables, then you go back to usual diagrammatic technique. So as I will hopefully show tomorrow, at least I will give you a flavor that all of this just comes out from path integrals the same way as you derive Kelvish technique, but you don't deal with diagrams. So you can just reproduce those results. So, but what I'm trying to reproduce is picture of motion in the phase space, and there I just don't know how to approach it. But there are lots of open questions, because we know that, for example, fermionic systems can have collective bosonic behavior. So normally we always start from quantum description, integrate out fermions, get effective bosonic theory, and then write some hydrodynamics. Maybe it's possible to do the other way around. Start from this Grassmann description, write out classical equations, and then on this level integrate out Grassmann variables. But I don't know. I don't think it's impossible, but I think people tried, they couldn't figure out. That's an excellent. I would leave it as a homework exercise. It's maybe a little bit too much. Good. Well, same by the way with tunneling. So when you go to tunneling, it's also a classical, obviously semi-classical limit, but I don't think it was reproduced in this language. So I'm pretty sure you can do it formally. Good. So I'm starting dynamics quite late, but it turns out that now I need, I guess, 1 minute to write down equations for the Wigner function. I go back to my von Neumann equation, bar is equal to h, hope we got sons, right? So the only thing I should do now is to do Weil transform of this equation, right? We did everything. We don't need to derive anything. Weil transform of the density matrix is a Wien-Wigner function. And Weil transform of the commutator, it was here, it's a small bracket. I'll use second quantized notation, so this will be I times coherent state of Moyle bracket of H, and W, M, B, C, small bracket coherent. Oh, sorry, there is no I here, I think. Yeah. Which is the same as 2 over H bar, HW, my sine of lambda C over 2 times W. That's it.
There is an H bar in the sign, right?
No, because for coherent state I define it without H bar. But when you deal with bosons, we normally measure energies in units of time, so we absorb H bar in C. Have second quantization, H bar plays absolutely no role. H bar is intrinsically hidden, because we remember that if we think about, say, thermal distributions, our number of particles is energy divided by H bar omega. So when H bar goes to 0, we automatically get large number of particles. But for us, large number of particles is initial state. So once we have large number of particles, for whatever reason, we have classical limit. H bar is just conversion unit between Hertz and whatever energy units. So it looks simple enough. So let's try to, oh, and there is no H bar here because, sorry, because in coherent, there was H bar when I used coordinate momentum representation. There's no H bar here. So, but I don't know what to do with this equation. Well, let me just be a little bit less general than usual, and just say that we always deal with few body interactions, right? So H will contain at most 4 A operators. Well, you can generalize it to arbitrary operators.
So when you define the Moyle product in coherent state basis, it was e to the minus lambda c with no.
Yes, so what we had is that, yeah, so let me write it here. So omega 1, omega 2, while plus omega 1, while e power plus lambda c over 2 omega.
So why is it sine and not sin?
Oh, it's sinh, you are right. Yes, thank you. Thank you. Yes. Sinh. So it means that we don't need derivatives higher than 4. So it allows us to expand sinh up to third order. So we don't worry. So what we get is HW lambda W plus 1 over 4 HW lambda C, sorry, lambda C cube. There's probably more, right? So we have, how does it go? It's x plus x cubed over 3, right? So we have x to 1/3.
Minus.
No, for sinh there is plus. It's from sine, yeah, I think it will be 3 times 4, 1 over 12 times 7. So this is usually okay. If you have more than 2 body interactions, you have to continue this. Okay, so let us just stare at this equation. So first, we note that if you close to a classical limit, if you have number of particles which is large, then this term is dominant. This has, if you want, 1 over n squared down. If I would do it in coordinate momentum picture, now I would have h bar here, So this term will be h linear in h bar, but that's okay, we'll have h bar here, so h bar will cancel. And next term will be h bar cubed. So when h bar cancel, so it will be down by h bar squared. So we just see that h bar and 1 over n roughly play the same role. So in the leading order in 1 over n, up to 1 over n squared, I can just ignore this. And if I ignore this, what I get is my Lewis equation for the Wigner function. Because remember, our starting point was equation of motion for classical probability function in the coherent state basis, which looked exactly like this, the first one. And we discussed how to solve it. Solution is trivial. We solve it by characteristics, but basically, if we have classical equations of motion, our fields for particles, they evolve according to deterministic trajectories. So we immediately can write that expectation value of any operator, omega, which now depends on t, will be just integral over my phase space variables w of a naught star omega of a of t omega while sorry a star of t. So this is not exact, but this is what's called truncated Wigner approximation. That's basically it. This result is the title of my lectures. Huh?
Where's the approximation thing?
So the approximation that I ignore this term.
I know, but in that expression, it's not.
Oh, here too. Let me just be, well, it depends how you interpret this.
Right.
So let me just maybe spend a few minutes. So we derive this result, but we, I guess, have to discuss what it means. So first of all, you immediately see, once again, Heisenberg and Schrödinger picture. Again, there is nothing quantum about these two pictures. Just in one picture, we think that our probability distribution depends on time, but our operators stay constant. The other is that our probability distribution is constant, but our trajectories evolve, and therefore operators are determined on time-dependent trajectories. So Heisenberg and Schrödinger picture are just this. They're completely classical. So they translate to this language. So if I work with Schrödinger picture, I will say that I'm solving this equation for the Wigner function, and then I substitute my Wigner function into whatever at time t and evaluate normal expectation value of my omega, whatever it is. It's more convenient to work in Heisenberg picture when I'm actually saying that I fix my initial distribution, whatever it is. Then I evolve according to classical trajectories, which are just characteristics of this, well, Liouville von Neumann equation. And then I evaluate my observable at this trajectory. So this A of t and A star of t are solutions of Gross-Pitayevsky, whatever, Newton equations with these initial conditions. So I'm just sampling over initial conditions and I propagate classically. Well, this approximation is extremely powerful. So first of all, I see that if my system is harmonic, it's exact. Because this term just vanishes. Yes?
Sorry, if you're saying that, then don't you want to be integrating over initial conditions, not over the time?
Oh, yeah. Sorry. You're right. Yes. So I have to integrate over initial conditions. So Leo is right that in a sense I can still write this in a general form, even without truncated Wigner approximation. But this object will be horrible path integral. Because I did not say what's A of t, but roughly you know that in the classical limit A of t is unique trajectory. Not in the classical limit, there are many trajectories. Yes?
But it's Jacobian as one of this transformation from A of t to A of 0.
Yes.
That's why.
Yes.
That's why the
That's the classical. Yes.
So what's the control parameter for this truncation?
1 over n squared. H bar squared. It's your
N is number of particles.
Here it's the number of particles, yes. or if you work in coordinate momentum representation, if you're on Planck constant. That's semi-classical. So another good thing, and that's actually where Wigner transform stands out of other transforms. I mentioned that you can have P representations, Q representation. So it stands away that the leading order is lambda cube. In other representation, you will do a correction of the order of lambda squared. Lambda cube is like extra h bar cube. It actually means that, well, it's down by extra order. So it means that even if you're interested in the leading order contributions, quantum contributions, we can still neglect this one. It's only 1 over n squared. So corrections 1 over n we can include in everything. So in this approximation, basically, our quantum mechanics enters in 3 ways. It's completely classical result, but there is still quantum mechanics. So first we use Wigner function, not classical Boltzmann distribution, which actually good because we already know it includes zero-point motion. So we can add zero-point motion in dynamics. So I mentioned in the very beginning that one, say, type of problems we might be interested in, say, parametric amplifications. And that's where parametric amplifications, if you start from a ground state, it's parametric amplifications of quantum fluctuations, because classically there is nothing. We can also think about these problems which I mentioned like that when we, say, break some symmetry. Then initially we have some zero-point fluctuations, and these zero-point fluctuations will be enhanced by classical motion. It's more or less trivial, because our Wigner function will have all these fussiness. And then we have classical evolution. So, of course, you might say there are all these classical fluctuations, but then you might say that this gives you a limit. So this gives you a bound. If you have extra thermal fluctuations, then of course they will dominate. But very often, especially if unstable degree of freedom is ultraviolet, for example, then the thermal fluctuations are negligible. But quantum fluctuations are never exponentially small. It's, if you want, 1/2 of a particle per mode. Just 1 second. And so next, quantum fluctuations enter while symbol of the operator. Like basically, when I write my classical quantum correspondence, I have to use symmetrized operators in simple words. And the third very subtle thing, which is normally not sort of discussed, at least in the Gross-Pitayevsky sort of language, it's never discussed, that I have to use while symbol for the Hamiltonian. This can be important in certain situations, and I'll show examples a little bit tomorrow. Was a question? So, what are the other situations when we can apply this? So, if I have time, I'll mention tomorrow that this not only exact, this approximation in the classical limit, but it's also exact in the short time limit, asymptotically exact. So the smaller the h bar, the longer the time when you can prove that it's exact. So this can be really useful for a large class of problems where, for example, initially quantum fluctuations are important. It's like a problem when, think about like sudden quench. So you have a system which you prepare in ground state, and then you just shake it, hit it with a hammer. And at short times, this is just exact. You just have classical evolution. You have to figure out what's the initial Wigner function, but after that, you have classical dynamics. But at long times, you start occupying many modes. You create quasi-particles. And if you create enough quasi-particles, then this becomes exact just because quantum mechanics is lost. So there are lots of, basically, this short answers that there are a lot of situations when this is really useful approximation. But of course, in some situations, it doesn't work. So now, again, without proof, the proofs are available in lecture notes. Let me say like another important thing. So this is basically if you're interested in some observable in time t. But very often we're interested in some correlation functions, length-time correlation functions. So what if you want to compute just arbitrary non-equal time correlation function, but just to be specific, let me just imagine that we want to compute A dagger of T1, A of T2 within the same approach. And first, let me imagine that T1 is less than T2. Well, if you think about this, there is no while symbol for this non-equal time correlation function. We don't know what it means. But what one can show is that this Bock representation becomes extremely convenient for this. Because I will say that my A dagger of T1 will be alpha star of T1 minus 1/2 d by d alpha of T1. I just add indices here. And same with A of T2. Okay, plus d by d. So I add indices, but now I need to interpret what I mean by this. And I will interpret in this most natural way. I'll interpret this derivative as response to a small jump in alpha. So basically what I'm imagining is at moment T1, my conjugate variable to A dagger, which is A, alpha of T1, has a jump plus delta out, where delta is some infinitesimal number. Then, if I use, it's by the way exact thing, but if we focus on truncated Wigner approximation, then I continue propagating it classically until later moment T2. And then I just evaluate response to this jump. So basically I evaluate difference between two trajectories, one with a jump, one without a jump, and take derivative. So obviously when T1 is equal to 2, I reproduce canonical commutation relations. Because if T1, so imagine that T2 is T1 plus epsilon plus infinitesimal thing. So my A, my alpha didn't have time to change. So it just jumped and then calculate the derivative to the jump, I get minus 1/2. But if I wait longer, there was a time to respond. And my response at a later time will be not the same as response at this time. So I will get, if you want, a different response, but which I can still compute using my classical equations of motion. So now what happens if I am interested in opposite correlation function, A of T2, A dagger of T1? So I'm still assuming T1 is less than T2, but now my earlier time appears on the right. Well, it turns out I can still do the same, there is no problem. But if I do the same, so the same I mean that I will have a jump at moment T2, which acts on T1, then I have a trouble with causality. Because I will evaluate jump at moment T1, sorry, I will evaluate response at moment T1 to an event which occurs sometime in the future. So there's no problem with this mathematically, but there's definitely a problem if we think physically. It just cannot happen. We believe, but some of us, I guess, believe that we have causality, which is fundamental. So this is exact, but it's useless. But now remember what I told you many times. We will use left Bock representation. So instead of right representation, I will now say that my A dagger of T1 will be alpha star of T1, but now 1/2 plus 1/2 d by d alpha of T1, but now it acts on the left. So what I will find, after that I can change back order, so I will find that this will be just average of alpha star of T1, alpha of T2, plus average over line will be average with respect to Wigner function, plus 1/2 d by d alpha of T1, alpha of T2. So here for this side, I will get correspondingly alpha star So I see as I expect from quantum mechanics at moment T1 is equal to T2. My my expectation, whatever A dagger A has extra one, jumping extra one. This is basically commutation. So there is a simple sort of interpretation of this, and we know it from uncertainty principle. So I'm speaking very loosely. I don't want to go to measurement theory, though I think this is really nice way to think about it without collapses of wave functions or whatever in phase space. So loosely speaking, what is this correlation function? I sort of measure A dagger at moment T1, and then I wait and measure at moment theta A. So that's sort of interpretation of this correlation function. I know if I do it classically, it's okay. I measure, I continue, I just always measure product of these two guys, and I average on initial distribution. But quantum mechanically, my measurement necessarily have a feedback action. By measuring alpha dagger, my conjugate variable sort of experiences uncertainty. And this uncertainty is reflected in jump. So, and therefore, I will, at later time, I will get correction. So basically, my trajectory is affected. So you see it immediately. So, and from this, we immediately see that if you want to compute anti-commutator, again, symmetric expectation value, even though it's non-equal time, I don't worry about these jumps, right? Because if I add these two lines, this plus this, I will get just average of alpha star. So symmetric expectation values still classical. But if I want to compute commutator, then classical part drops out, and the only thing which survives is this jump, A of T2. So if you wish, this is like a non-equal time correlation function. We can interpret this, at least in the semi-classical picture, as a response to a jump, like in the previous. Of course, this is like interpretation, but I think it's very convenient. When T2 is equal to T1, you get 1. It's usual commutation relation. But when you just can ask what's the meaning of the commutator in this classical language when T2 is not equal to T1, well, it's delayed response. You just jump, then wait. So it's sort of loosely speaking, you see that why at long times commutator vanishes, right? Because if you have a jump and you wait very, very long time, you will completely forget about this jump. There is no way, because if you deal with many multi-particle system, there is no way you can remember about this jump. So, oh, I think I should be done, so just give me a few seconds. Yeah, so I think then tomorrow I'll start with simple examples, like analytical examples.